now we're talking about emotion work carried out students. Um, so facial expressions actually represent a big part of nonverbal or implicit communication. And so when we study facial expressions, we can have a good idea on emotions. So facial expressions are right for voice about emotion. And so in computer visions, there are many ways to categorize emotions. So the most popular way is Ekman's categorization, the seven main basic emotions. We can also talk about the other two models. One is fact, like facial action units, and the last one is balance arousal or balance arousal and dominance. So more and more applications actually automatic facial expression recognition. So for example, HI, security, health, etc. And so classical facial expression recognition models are based on different steps, so face detection and landmark detection, feature extraction, and then facial expression classification. While deep learning based models are mostly based on CNNs. So first I will quickly present a little benchmark we did on some open source CNN models for facial expression recognition. So we compared 4 open source models on 4 datasets. So we'll describe them a little more. So the datasets, the first one is JAF. It's an in-lab dataset. Some Japanese female who post expressions like happy, sad, etc. It's a quite small dataset with 213 images. It's pretty much well balanced in terms of emotions, and all images are grayscale. Then we use so 3 wild datasets, so images taken in a while, not posed. All of them are constituted of images taken from internet, so with more or less images and more or less balanced, as you can see. As far as the open source libraries are concerned, we used 4 Python libraries. DeepFace has several models, so not only facial expression recognition, but also age, gender, and race. It has one specific CNN model for facial expression recognition. PyFit is composed of 2 CNNs and 2 classical models. So we use the RMN, so residual mask model of PyFit. MOPy has 6 CNNs. So actually what they have different is the different output size. Some of them give out 7 emotions, so 7 basic emotions, while others only like 3 emotions. And then RMN model. So results. Well, we can quickly see a few things. The first thing we can see is that the results are not great. So with accuracy around 50%. Then we can see that quickly that RMN is the best model on JAF dataset, and DeepFace the best one on FAIR, and RMN again for RUF and AffectNet. So yeah, overall results are not very high. We had a look at different metrics: precision recall, kappa-Cohen, F1 score. Overall, and then for the best model for each data set. We had a look at the performance on each emotion. So again, we can quickly see that some emotions are easily predicted, or at least more easily than others. So usually happiness, neutrality as well, sadness, and surprise were better detected. So for RMN, we had a high precision on happiness. So deep face was the best model on fair, so was fairly good for happy images, but not so great on others. Similar results for RMN. So all the models were fairly bad on disgust and fear emotions. And so now what we are going to do is we want to create a new experiment, a new comparison between humans and deep neural network models based on the work of Samuel Dodge and Lina Karam. So what they did is they compared the performance of humans on PNNs on object recognition on distorted images. And so we want to do the same, but with facial expression recognition instead of object recognition. So for that, so far we created a new data set. So we took 140 original images from the FAIR 2013 database. So we chose 20 emotions, no, 20 images per emotion. And we applied 3 distortion types, so Gaussian noise, Gaussian blur, and salt and pepper noise on these images at 3 different levels. So in total, if we count the original images, we have 1,400 images. So here we have an example of an image, so an angry man with Gaussian blur, so original image, and the 3 different types of distortions. So what we want to do is we want to ask some participants, human participants, to say which emotion is on the image. So they will have to choose between the 7 emotions and to give their confidence level on a continuous scale between 0 to 100. And so what I just said. So then we want to compare these humans with deep learning models. And so far we haven't started the human experiments, but we have started to have a look at the models. So we will use 2 different models, DeepFace and RMN, which were the best ones in the first benchmark. So we will use the pre-trained model, the ones which are open source available, and some fine-tuned models, which were fine-tuned with distorted images from, well, not from our dataset, but from like the same datasets in FAIR 2030. So what can we see on this image? We can see that RMN pre-trained model dropped very quickly in terms of accuracy with the different noise levels, but fine-tuned models seem better. So the next steps will be to have a look at more results and compare with basic. Thank you.
Good. Questions? More like a comment than interesting, true. And I really looking for seeing the results of humans for no discussions.
So usually, depending on the images, the human accuracy not perfect either. So I saw something around 80% on original images, but it depends on the data as well. And so on this sort, I wonder how it will look like.
Do you expect the categorical performance difference in terms of emotions? Or
Yeah, so I would say that, well, even on original images, like maybe happy images are easier to find. Fear and disgust, we don't always see the difference. So even for humans, I think there will be difference.
is there an intensity level of emotion on facial expressions? Because from what I've seen on the images, I can say that some are more intense than the other, but their data set is that kind of information.
Not at all. So on most of datasets, it's just one gun truth with one emotion out of the 7, and so that's actually something we raised up, like that. Maybe it would be good to have a percentage of emotions on one image, because maybe you are not 100% happy or 100% angry, and actually the models don't give out a ground truth. I mean, one single emotion, they give out percentages of the 7 basic emotions. So, yeah.
So maybe suggestions that would maybe help have better accuracy. Maybe if you that detect some points on the face, like for example mouth, noise, ears, and so on. Maybe if you use this kind of features, after that detect if there is any.
So these I think are linked to the FACT system, so facial action units, and so they are different kind of models, which are based on the movements of the eyes, mouth, the nose. So these models are not based on that, but
could be an idea.
Yeah. Irene, other question?
Yeah, I was wondering if you were thinking about how you were thinking of the confidence of the thing, because I think it's a very interesting element.
So that's actually a good question. If you have any ideas, so maybe it could be used as some kind of weight.
Yeah.
So on the human decision. So if they are like, okay, I'm 100% or 5%, the same, and so this would definitely be something to consider.
Yeah, I was wondering if it makes sense to add more than one emotion related to what you were saying, that it's not so like to say like, okay, if I'm not 100% confident, then what would be the second one that I would say or something. But I don't know if it's very complicated to add.
So then it would be a matter of timing of the experiment.
Yeah, I understand.
But that's or maybe if like the confidence below a certain level, like below 20%.
I also wonder, the database contains only faces or different, like the natural.
So the four ones, yes, they only contain faces. But we noticed that a few images among the big database were actually not faces; they were completely random stuff, and so we removed them. So maybe they were not checked, but it's not all body; it's just faces.
Okay. And the other question is, did you consider to make the test selecting images where the artificial intelligence, like the methods detect correct emotion, at least for the soul side, and then we start to talk, because to some extent you are testing two different things. One is the accuracy of the system that could be improved in the future, and second is how it.
So no, maybe we're not correctly detected by the model at first. Also to see if humans can actually recognize the emotion or not on this image.
So the prediction will be multi-level or full level. So for example, our image will have only one emotion, or maybe because I think
the models will predict 7 emotions percentages for each emotion. So like it will say, I don't know, happy 70%, angry 1%.
So the ground truth is for one image is only one emotion, or
the ground truth is only one emotion? Yes.
Okay.
Yes.
Okay.
So
because Because I think in some cases it's more in the emotion will be the combination of
Yeah.
two.
Yeah. But all these data sets, they only have as a branch with one emotion.
Okay. And there are no questions. I think wrap up the first Cracovia session, and the remaining second part will be on Thursday after. Only one presentation is going to be out. So I think it's break time.
Okay. Yeah, I think. Yeah, maybe it's a good time to have a short break, and then we go with some. So let's 15 minutes and be back 4:40.
Okay, and we have 5 presentations, so just quickly jump into a I already see that the order of the presentation is different than it was written in the file, but
You can take it any order you want, since you're in the share of some sessions.
yeah,
Let's
yeah,
go ahead.
let's go ahead.
The first one in the
Okay, no problem.
Are you connected to the Zoom?
Yeah. So I don't know.
Then
I
if
just
you share
share,
it, will
but I mute.
Yeah, you mute. You will that thing there will pick hopefully pick up. Yes, now it.
So hello everyone, I'm Andreas Pastor, and I'm first year PhD student from University of Nantes. And the work I want to present today is one of the early work of my PhD thesis. So the title is Improving Maximum Likelihood Difference Scaling Method to Measure Intercontent Scale. So maximum likelihood difference scaling, the subjective methodology. And the presentation will be divided in 4 parts. So about the motivation of that work. So first, a quick overview of my thesis. So the title is Lightweight Localized Video Quality Metric for a perceptual approach boosted by computer vision. So what does it mean? It's about developing metric for localized spatial and temporal at a spatial and local temporal horizon to lead the decision in the video codec. And what we already know about is that there is a multiple metric existing for large scale, large horizon entire videos like VMAF, and so on. And what we are currently trying to address is distortion in codec and at a local scale. So what is already existing this day is a metric that are inside codec and that are computing pixel-wise difference, but these metrics are not tuned for the human visual system perception. So I will also present the importance of perceptually optimized video coding and how it's related to the human visual system. So video encoder take decision at coding unit size, and the rule
of human eye perception is at a special location that is 1 degree of visual angle, so the fovea, and temporarily located around 100 milliseconds that correspond to a gaze or fixation. And these gaze are aligned with the direction of an object that you are tracking with your vision. So what this work is interested with tubes. So what we call tube is localized temporal on the temporal and spatial horizon of short video clips that are following objects. And I could also quickly give an example. So what you are doing in the encoder is you are starting from a reference frame, and then you are dividing in the coding unit, and the encoder will generate different candidates for that CU. And what we want is to have an evolution between the compression strength. More you compress the coding unit, and the fidelity compared to the reference block. And this, you can do it for all the CU in your frame, and you will get this intra fidelity curve. You have a fidelity compared to reference for each of the CU, and we call that intra scaling. And what we are interested in is also to have the inter CU scaling. So how the one CU is robust or can handle more heavily compressed compression compared to another CU. So where we can compress more in a frame. Okay. And to do that, we need to have a subjective methodology to collect this kind of ground truth data. So how can we collect this ground truth data? There is plenty available subjective methodology. So which one are interesting, which are also efficient, and how we can solve to estimate this perceptual distortion. So maybe you're already aware about different methodology, pairwise comparison. And on top of this methodology, you can have a boosting strategy to sample efficiently some pair and reduce the cost of an experiment to estimate quickly a numerical value for each of the stimuli. And then there is also other methodology based on quadruplet, triplet, or two alternative for choice. And this is what we will go for in this work, but I will describe in more detail. And to assess and estimate numerical value for each of the stimuli based on this subjective methodology, there is plenty solver that can estimate these values. So maybe some are familiar with Bradley or Sosthenen model, and what we're interested there is maximum likelihood difference scaling solver that use GNN. So why we want to use maximum likelihood difference scaling? So in our case, we have a pre-ordering of the different stimuli, because we start from a reference block and we will increase the compression. So we will increase the perception on the distortion. So we can have this pre-ordering and this information beforehand when you want to collect data. So in that case, MLDS is leverage this information to sample interesting quadruplet and avoid to try to evaluate all the combination of quadruplet that you can generate from your. So numerous research work are using this methodology, like for audio or for different different domain, and there is some benefit. You can have a better discriminative power, like when you are doing pairwise comparison compared to direct annotation subjective methodology. You can also reduce the cognitive load because you are just comparing two stimuli and not trying to assess an overall quality or comparing. And you can try to boost the number of trials that you need to annotate to have a good estimate. And one of the disadvantages of MLDS, current version, is that this perceptual scale, you can only retrieve it for intra content estimation. So in our case, it will correspond to a different encoded version of it. You will retrieve for only that one, and it will be bounded between 0 and 1. But us, we want to compare different perceptual scale. So the remainder of the presentation will be about procedure to enable MLDS. So MLDS. Okay. I have the procedure is based on a quadruplet, and people are asked to perform a judgment. I think it's an important slide.
No, just
Okay, so you can see an example on the right, there, of a kind of a question that you can ask to participants. Where do you perceive a difference between the lower two and upper two patches? In our case, we cannot see through Zoom, but the answer is over there. There is a larger difference between this version compared to these two.
I think it's better if you use the laser pointer on the presentation and circle, then they can see also online. You able to get the laser of the presentation, right?
No, it's okay. It's okay. Okay. Always okay. So, and then what you will store in a matrix is the index of the stimuli that has been presented to the observer. So that's why you have 1 and -1 that correspond to the position in the stimuli. And in the first column, the answer of the judgment. So either 0 top pair of patches or 1 bottom pair of patches. And based on this data that you collect, you can use a generalized linear model to estimate numerical value for each of the stimuli. And what we are proposing in our paper is to add and enlarge this matrix X to contain inter-content comparison, so quadruplet that will made up of two stimuli from one content, two stimuli of another content, and people will assess where they perceive the largest difference between the pair of patches. And we can construct larger matrix like that will contain sub-matrices of intra-content comparison. And for instance, in the two last row, you have example of inter-content comparison. And you can solve based on that using a modified version of PLM. And to validate if this procedure is converging and is efficient, what we've done before collecting subjective data is to simulate annotation on the ground truth designed content. So we design content. So we design ground truths. So each of the ground truths are represented by mu and sigma to create a fake distribution of subjectivity in the ground truth value of stimuli. And what we will do is sample judgment based on the quadruplet that will be sampled from this generated distribution. And what we propose to evaluate the solving power of our solution is to compare the RMSE between the simulated ground truth and the estimated value for the ground truth. So we have the ground truth on one side. We will generate, let's say, 1,000 annotation on them, and then we will compare if our solver is able to retrieve the same mu and sigma for the description that we generate. And so I quickly the slide, but maybe you are more interested to tell in the paper about the methodology. So we propose a methodology that is sampling smartly quadruplets, and we compare it to a version where we sample all the possible quadruplets. So there is a lot, and so it's not efficient to perform like that. And the methodology that we propose is able to save up to 40% of annotation. So that means that you will have the same precision with our methodology, with 40% less annotation compared to the naive approach of sampling. So we can collect more data. And after, also in the paper, if you're interested in, we are also simulating spammer behavior by inversing both a judgment on the quadruplet and emulating some spammer behavior to see if our methodology is also robust against outlier behavior. So to conclude, in my PhD thesis, we are interested in human perception to drive encoding. And there is this really huge, how to say, not problematic, but characteristic of the work that we have intra and inter content comparison, and we need to relate all of the information together, take good decision for that. And the first step my PhD has been to propose the expansion to already objective methodology, be able to collect this kind of judgment. So in future work, what we want to do, and I currently almost finished that, is to benchmark this proposed methodology compare with other subjective methodology like pairwise-based methodology, and to see also if it can work on real data, like we collect real data, and we want to apply that to collect obviously large scale. So yeah, thanks for your time and your attention.
Thank you very much. Are there any questions? Online questions? So we can
take
online
questions.
Can you ask your question?
Yes. Thank you very much. I was wondering about your simulations. You ran the simulations with this probabilistic model that the stimuli have a distribution of qualities that are Gaussian. Now, and you're using this for MLDS, but MLDS has its own probabilistic model for the responses. Namely, it would say that if you have a quadruple and the stimuli are A1, A2 and B1, B2, then the decision is guided by the following. You take the difference of A1 minus A2, absolute value, and the other difference, and you subtract the two differences. And if that is positive or negative, that's a decision variable, then the outcome is accordingly, left one or the other. But there's also then a normally distributed random variable added, which makes it a probabilistic outcome. And you could have used that particular model for the probabilistic responses that is used by MLDS in order to ensure that in your simulations, you can ask for a convergence to zero of the error, right? you should converge to the same model, to your ground truth. While if you have the normally distributed ground truth that you have here in your model, you cannot ensure this. So your convergence will stop at 10 to the -3 or 10 to the -4 or so, as you have shown on the other slide. So my recommendation would be to try this out with this probabilistic model from MLDS, and then to check whether your curves really go down to 10 to the -infinity, so that you at the end can approximate the ground truth arbitrarily closely.
Thanks for the feedback. I will take. I will try to understand what you mean by that, but. But I saw in the MLDS that there is this kind of effect, but yeah, but yeah, okay. I will try.
It's not a crucial thing. It's just nice to have convergence to the exact ground truth. Yeah, that's just my recommendation. Mhm. Thanks.
Okay. Thank you very much. Another question? Not, then we can go on.
So my name is Jakub Nawała. I am a PhD student at AGH. I'm not the only co-author of this work. Lucja, Bogdan Chmiel, who is our statistician colleague. We also have here Krzysztof Rusek, who is also a PhD publisher. So I will talk to you today about the generalized work that we submitted. IEEE transactions on multimedia. We already first round reviews. So we got some remarks, we addressed them, and paper back to the second round of reviews. What is important here is that the results that I will show you today were not challenged by the theory. They asked to look from different perspectives, also see other aspects of works. At least we can say tentatively work peer review. You have here the idea of the preprint. I will only show today a very portion of work. If you are interested in more details, then I'm referring you to the timer. I'm on time. Okay. So let's start. The general background of our work is that we want to use a distribution model subject to response. And when I say subject to response, I mean a response given by a single subject to a single stimulus, for example, a video, during the subjective experiment that uses the 5-level ACR scale. We have only 5 categories, and each person is able to give only one score, numerical or rather categorical score, to a single stimulus. So we want to get as much information as possible from that data. So we as a community like to use the ACR method, but terms of data output, it's rather simplistic. Just have single digits for a single tip for a single stimulus. So we want to get as much information as possible from those single digits. And of course, we usually use MOS, but we argue that it is possible to use a more sophisticated method that is still simple and interpretable as the MOS. And another aspect important here is that we want to reflect the discrete nature of response. Because even when we use MOS, we implicitly assume that what we see is not really an ordinal variable where we know the ordering, but we do not know the distance between categories. When we compute the MOS, we implicitly assume that this is a ratio scale. We can assign numbers 1, 2, 3, 4, 5, and we assume that we are sure that the distances between those numbers are constant, which may or may not be the case. And to give you the main idea, I would say the main idea here is to convince you or the larger multimedia quality assessment community that using the GSD, so the generalized score distribution, does bring a serious benefits compared to the current methods. And those benefits span greater interpretability. GSD also provides a good description of the data, and we argue it also provides greater generalizability. By observing, you want to observe a small sample of your population of observers, but you would like to make inferences of the larger population. So what is the GSD? I will call the GSD a model, sometimes a distribution, but in principle, it is actually a family of probability distributions, or actually three probability distributions. It has only two parameters. So the first parameter is psi, which is a central tendency of the data. I will later argue that you can treat it as an MOS equivalent, something close to mean response of participants. And you can also understand this as a true quality of a stimulus. So in statistically speaking, you can say that psi is the mean response you would get if you ask the complete population of observers about their opinion. And the second parameter is rho, which is response spread, which is actually a confidence parameter, meaning the higher it gets, the less is the less spread the responses are. We can see here that GSD is somehow similar to the Gaussian distribution. So we have two parameters, one related to spread and the other related to the central tendency. One more thing I should say here is that U here is a discrete random variable, and it represents a single score assigned by a single person. So I said for one of the 5 categories. And here are examples of few distribution shapes that GSD is able to take. So as you can see, we have pretty standard distributions like the one in the top left corner, which is many responses of category 1, fewer 2, 4, 3, 4, 5. But the GSD can also take pretty unusual shape, but which we also do sometimes see in subjective experiments, which is the U-shaped distribution, or as we like to call it, hate or love distribution. So if you look at the green boxes or green squares at the bottom plot, you can see that there is a highest probability of 1 and also the highest probability of 5. And another thing to notice here is that scores are generally accumulated around psi, so the central tendency, and the lower the row gets, the responses are more spread, or the other way around, the higher the row, the responses are closer to the mean. Maybe I will skip that, I believe. Yes. And the distribution we compared the GSD to, so-called ordered probit distribution, or the quantized normal distribution, which is somehow popular in the MQA community, but it's for sure very popular in the psychometrics community, also used in econometrics. So you can argue that quality is something that is influenced by multiple factors. You can take this physics approach and say, okay, if it's influenced by multiple factors, then it probably has a Gaussian distribution. This is what you see in the lower display. You can say that there is some latent feature of a stimulus, for example, a video that you would like to observe, and let's say this latent feature is quality. But what you and you say that this feature has a normal distribution. So what you see on the lower display is actually a continuous distribution, a distribution of quality. And now what people do is they map it to a discrete scale, because the discrete scale is what you do observe in ACR experiments, and this is what you see in the upper panel. So you basically take a portion of the latent normal distribution, calculate the integral, and say that whatever you got under the curve, the probability of a given response category. So for example, the mass, the probability mass here below this curve translates to a certain probability of a discrete response with category 1. And of course, you can change the shape of this latent normal distribution by changing the mean value and the spread or variance parameters. So you control mu and you control sigma squared. And one thing I should notice here is, unlike this figure, we do use constant thresholds. So here you can see that the intervals used have different length. We don't use that. We use constant thresholds in the middle between response categories 1.5, 2.5, 3.5, 3.5, and 4.5. Now, I would like to argue that PSD has interpretable parameters, and to understand that, we generate this figure. So let's focus only on the upper row of this figure. So what you see on the left, so what you see here, are parameters of ordered probit distribution. So on the x-axis, mu, so something related to the central tendency of the latent distribution. And on the y-axis, you have sigma, which is related to variance, which actually is variance of this latent distribution. And now, in your subjective experiments, you observe discrete responses, as I said, and because they are discrete, they are limited in terms of mean, but they are also limited in terms of variance, because you can only go from 1 to 5. Plus, mean is also related to variance. And the shape, this ghost-like shape, is this ghost-like shape is exactly this limitation of mean and variance, and also the relationship between mean and variance. And to understand this plot, let's take one point in the left panel. So let's say we focus on mu equal 4 and sigma equal 2. And now we take this point, and thanks to this point, we are able to map to the discrete domain, generate response probability, so probability of each response category. And from this, we can calculate mean, and from this, we can also calculate variance. So this point here is mapped to the point on this ghost-like shape. What I should have said is that on the x-axis of the ghost-like shape, you have mean, and on this on y-axis, you have variance. But this is the variance you observe in your responses in a subjective experiment conducted with ACR method. The first thing you should notice here is that in order to cover the entire range of mean responses from 1 to 5, you must use mu that exceeds the 1 to 5 range. So it would be tempting to think that mu is somehow an MOS equivalent, but it is simply not, because in order to have a mean response close to 1, you actually need to go with mu below 1. This means that interpretability of this ordered probit parameters is challenging, at least, to say the least. The second thing you should observe is in this in this left display, we show vertical lines. Let's take the leftmost line. This line corresponds to keeping the mu constant. So you say, I want to keep the central tendency of my data constant. I only want to change the variance or the spread of the response. But if you map it to the discrete domain, what you get is a curve actually which bends. So even though you said, I want to keep the mean response constant, but you got a changing mean and changing mean here, but also changing the change in variance. So the change in variance is okay, but the change in the mean, not okay, not what you expected. And of course, I walked now this way from the model to the data, but under typical circumstances, you first have the data, so the results from your subjective experiment, and then when you apply the model, you get only two parameters. So what I'm showing here is that you should not trust the parameters you get from the ordered probability model or quantized normal model. And what I would like to argue here is that for the GSD, this is not the case. I mean, GSD does not suffer from the same limitation. So if you say, I want to keep the central tendency of my data constant, I only want to change the variance of the data or the spread of the responses, this perfectly maps, or rather elegantly maps, to what you observe in the ACR data you get from the experiment, and the other way around. When you fit the GSD data for subject experiment, you can be sure that if the psi stays constant or if the mean stays constant, it also corresponds to the constant central tendency of the data. And the second observation is that psi is always bounded to 1 to 5. So in order to cover the entire range of responses, to keep psi 1 to 5, psi always corresponds to 1 to 5, and the same is true for the data you observe in the subjective experiment if you fit GSD to this data. And this is just one of few aspects of parameters interpretability of the GSD. For more, I am referring you to the preprint. Now, the reviewers of our paper argued that maybe what we did is just a theoretical consideration of the model properties. So they asked us to check how in practice the model would work on real data. So in this paper, we took 31 subjective experiments, if I remember correctly, which amount to more than 1 million individual subjective responses. But what I'm showing here are results of only typical multimedia quality assessment experiments. So if I say typical, I mean laboratory experiments with a control environment following ITU recommendations, and so on and so on. So the stuff that PQUIC usually do for standardized experiments. And what we compute here, we take those experiments. For each experiment, we take all the stimuli, and then we focus on responses assigned to a single stimulus. So we always work on a per stimulus basis. So for example, only on responses assigned to a single video. And of course, if we have those responses, we can compute the mean, we can compute the variance, and we get two coordinates. So we get the mean, we get the variance, and this maps to a single point on this ghost-like shape. So what we can see here is that most response distributions, or per stimulus response distributions, I should say, accumulate around the lower part of the figure. Also, the observable variance between 0 and 1.5. So two important observations. First, it's important to notice that those true mean responses, or mean responses coming from actual experiments, do span the entire range from 1 to 5, which is obvious, but is of course important for this analysis. And the second thing to notice is that those points cover the area where the vertical lines end, which means if you analyze typical subjective experiments and you use models like ordered probit model, you will see inconsistencies that I showed in the previous slide, which simply means that you can get confused by using such an approach. Good. Now, I don't have time to go through the entire bootstrapping section. So what I will say here is that we also tested what we call generalizability potential. So in the ideal world, you want to make a small subjective experiment. You want to invite, for example, 20 people to a laboratory, gather the responses, and then using those responses, you can say, you want to know what would be the behavior of 100 people or 200. And you can then ask the following question. So if I gather those 15 responses, then I fit my model to this data. And I simply change one model parameter, which is sample size. So even though I fit it to the 15 responses, what happens if I change the sample size to 100? In other words, is the response distribution that I will get for those 100 responses, does this really reflect the response distribution I would get if I invited 100 people? So basically, you want to ask 15 people for an opinion, but infer what would happen on the larger scale. And unfortunately, I don't have time to go for this analysis, but the conclusion here is that the GSD is better than the ordered probit in case of generalizability, but it is also better than empirical. So what I mean by empirical distribution, you can take responses from those 15 people, focus on only one video, and say, okay, I see 5 responses 1, 3 responses 2, and so on and so on. And you can say what is the probability of observing each response, and use this one and say, even for 100 people, this will stay roughly the same. So if you fit the GSD, you will get more reliable results than if you use the empirical distribution or if you use the ordered probit distribution. So to the best of our knowledge, if you would like to extend your data, so you tested 15 people, but you would like to make inferences about 100 people or more, the GSD is the best you can use, at least for now. So I have picked that. And if it comes to conclusions, the GSD should be preferred over the empirical distribution when resampling responses. So in case of this generalizability test. And as I said, this opens up a possibility of using small sample sizes to generate larger data sets. And it may be important because in order to use machine learning and especially deep learning methods, you need a large data set. Using the GSD, you have a potential now to generate larger data sets by just observing a small sample. And discussion and conclusions, we argue that GSD's parameterization is intuitive and less error-prone. And as I said, it should be preferred over empirical when it comes to generalizability. What is also important, it describes response distributions observed in typical MQA experiments well. And to be more precise, it's the only distribution we investigated that does properly, in terms of statistical goodness of fit, describe response distributions we see in typical MQA experiments. So if you take our results for granted, the message would be, don't use other models, because the GSD is the only one that can describe data properly. And the last but not least is that the GSD outperforms, I should say, the modified version of the state-of-the-art model in terms of both goodness of fit and bootstrapping capability. And not to make the picture so perfect, I at the end have to say about limitations. So GSD is discrete in nature, which also means it does not work on interval data or continuous data. So if you take discrete responses and remove subject bias, and then you would end up with continuous data, then you cannot apply the GSD. And we are working on addressing this problem by adding the GSD, by adding the subject bias internally to the GSD model. There are more shortcomings, but in the interest of time, I will not go through them. And I also have to thank Netflix for sponsoring the initial part of this research. Anush from Netflix specifically, because we also used the data from subjective experiments conducted in cooperation with Netflix. Also, a big thank you to Zili for providing comments on this work. The work was also co-financed by Norwegian Financial Mechanism, and we also used, at least partly, the PL grid infrastructure, supercomputer infrastructure in Poland. And this is all from my side. Thank you.
You? With question? You have any question?
Yes, hello. I have a question and one remark. Let me start with a question. So you pointed out.
Can you ask your question? Yes, please.
Yes. So my question is the following: if you went to great details explaining the GSD and pointed out that it works very well in terms of generalization power and so on, and it is one out of zillions of possible two-parameter distributions for a five-dimensional or four-dimensional space of probabilities here. And what makes this this GST so special? You could have chosen many others. You compared it only with the ordered probit, but not with others. So I wonder if you had some guiding principles here that would, that led you to precisely this one and to no other ones. So this is this one question, and the remark is that if you go to page 8 on the slides, where you explained the interpretability of the models here. It was mentioned that in the GSD you have these straight lines in this parabolic shape here, and you don't have this in the order probit. That's all very true, but it's not the whole truth. You could just reparameterize the ordered probit model so that the picture on the lower right for the GSD is also valid for the ordered probit. Only then you wouldn't call it mu and sigma, but you would have a reparameterization. You would have mu prime and sigma prime or so. But then the interpretation would be exactly the same, only that in the background you would have to have this parameter transformation. So clearly you're correct in saying that the mu and the sigma of the order probit have less interpretation power than the psi and the rho of the GSD model. That's true, but you could fix this problem by reparameterization. So that was the remark. But the question was, why is this GSD so special? Is it the only one that one could think of, or are there other options? For example, if you go to the MATLAB and to the library of distributions there, so continuous distributions like the Gaussian, you could take any one of those 20 or 30 of those and apply the same procedure as for the order probit, define the thresholds, and then work with the two-parameter problem, work with a two-parameter distribution that way. That might also give you an alternative which might work even better than the GSD. So maybe you tried out this, or maybe you have some basic principles that led you to the GSD. So maybe you can elaborate on this a little bit.
Thank you for the remark. I really liked it. I like it. And yes, I think it's true that we could, in principle, reparameterize the ordered probit distribution, have the parameters that follow the GSD behavior. I'm not sure if this would retain interpretability, but yes, that's true. If it comes to why we chosen the GSD, we wanted to avoid this mapping from the continuous latent domain to the discrete domain. We wanted to use a distribution that is discrete and doesn't require this mapping from the continuous domain to the discrete domain. If it comes to using other distributions, as far as I know, it would be difficult or almost impossible to find a two-parameter discrete distribution that would mimic the behavior of the GSD. So I would say discrete two-parameter distributions are out. But if it comes to continuous distribution, if you would like to retain this mapping from the continuous domain to the discrete domain, then I agree. In principle, you could use any two-parameter distribution, try to map it to the discrete domain and check how it behaves for multimedia quality assessment data. So it is possible. We did not do it, but of course it's possible. And the one reason why we didn't do it is because ordered probit is such a popular model. We decided to use this model as is, and it turned out that it is much worse, or simply worse than the GSD. So we stop there and say, okay, there is an advantage of using the completely discrete model. And the other thing, did I answer the question as well? Because
Yes, yes, thank you very much. Fine.
Thank you.
Okay, so Irana?
I was just wondering if you have any code available in order to there's packages. And
I will repeat the question. Thank you. So Irena asked whether there is any code available. So yes, we do have a repository, public GitHub repository. It's the link is in the paper. Yeah, it's a shame I didn't put it here. Although I have to say here there is a disclaimer. The code there, I mean, there is a code, but we haven't yet prepared it for the end user. So everything is there, but you may find you may find it slightly difficult to use it, but we are working on it. We decided to first finish the paper, answer to the reviewers, and then work on the quality code. But yes, in principle, we do have a repository.
my suggestion would be to maybe make packages also, for example, for art. And not just the code, but also packages for people. I think especially in statistics, there's functions that are already pre-made that can be used.
You're right.
I will repeat what Irena said. Irena said that we should think about creating a package, for example, an R package from code. Actually, having our work on archive already helped because there is one guy who decided to reach out to us, and this is just his hobby to implement probability distributions, and he said if we provide him guidance, he will implement, I don't know, R probably as well.
I have another comment, but I'm a bit out of my depth. Which is, what about after using this distribution in order to model the data? What type of statistical analysis can you apply on it? Meaning that, like on normally distributed data, you can do ANOVA and you can do types of statistical tests. This is a discrete distribution, which means that you can make some sort of statistical test, but I don't know if you tested whether non-parametric tests, for example, also work for this type of data or you want to.
Yes, I will repeat the question. So Irena asked whether we can use what kind of statistical analysis we can use after the model is applied to the data. For example, ANOVA or any other statistical tests or other things that are available for standard.
So just answering quickly, the moment we believe that this distribution models well the multimedia data, we would be able to create a statistical test based on G. So it's not like we can use another test, but this distribution could be used as a base of creating the test. But this is again something as a future topic. The moment we would do that, this test would be more powerful than t-test, so and more accurate.
That was my guess.
It has to be created. Yeah, so not like already done or super easy.
Amen. Thank you.
Yeah, we have to fit definitely.
Thank you very much.
Thank
For
you.
all the questions, comments.
Yes. And Ali now. Yes.
What do you want?
Share the screen.
Yeah, I just
And thanks to that, you have this nice reply and think about what to say.
This is the verse.
Yeah, I like a bar system.
Okay, so today the presentation will be about spammer detection on pairwise comparison experiment, and we'll do this on different preference of experience scenarios. Basically, it will be a study, comparison study between two use cases that we will eventually make some conclusions toward identifying spammers in potential spammers in pairwise comparison experiment. But first, I should give some background. I'm pretty sure lot of you already are very well aware of what I am talking about, but for those who are not, so there are mainly we can divide the categorize subjective experiments into two tasks as rating and ranking tasks, let's say. Rating tasks can be simply an ACR where we have a verbal or a numerical category on a discrete scale, and we rate the quality of the stimulus that we saw at that moment. And this also can be done by a ranking strategy where we can observe multiple stimuli at once and rank them in terms of quality or whatever the quality of experience scenario that we are measuring at that point. And the most common way of doing this pairwise comparison experiments, where you see two stimuli at the same time, and you are forced to make a choice among the two. So either the left one has the higher quality or the right one has the higher quality. And this simplifies the task a lot, and it has a very high discriminative power. However, it has a few drawbacks, and the most well-known drawback of this scenario is also Andreas, 2 presentations ago, quite nicely explained his work towards a similar problem, where when you increase the number of stimuli in comparison, the number of pairs needs to be compared grow exponentially. So when you have 10 pairs, 10 stimuli to rank on a continuous scale, you need to make 45 unique comparisons at each time, which can go wild with more and more stimuli. So to prevent that, there are certain methods, but this is not the scope of today's work. We assume a full design here where you make all the comparisons and you have such data in hand to move on. But nevertheless, still there is an issue, and this will be the main topic that we'll address in the presentation, is the outlier detection tools, which we lack in the standardization efforts and in the literature for pairwise comparison data. And the main challenges to come up with such tools is actually lies on the binary nature of the pairwise comparison data, because unlike ACR experiments, etc., or other rating tasks on a continuous scale or a discrete scale, where we have how far your answer is from the rest of the population, can give us a lot of information, but in this case, on a pairwise comparison scenario, I only have a binary choice. Either I say left or right, or I say yes or no, which doesn't tell me how wrong I am or how right I am. And this can be more challenging for stimuli where the half of the population choose one side and the half of the population choose other side, which doesn't tell anything about the reliability of the observer. And this also makes it to both statistically and verbally make it difficult to define to draw the line in response, which is becoming more and more difficult. So to evaluate some aspect of this strategies and to move towards the standardization tools or methodology, we conduct 2 experiments, and with of experience and observers are presented with I don't know why you don't see them.
We are
Okay. Soon you will see here as well. So on the right there is preference, and on the left there is a tone mapped image quality experiment. So the names are XBP and XPMO from now on. Yes, great. So you have on the first experiment, you have 2 stimuli, and you have to choose the one that represents the 3D object the most. So basically, we select 4 different views from the 3D object, 3D mesh, with the textured 3D mesh. And and we ask the observers at each time for a viewpoint, which for this question in more time that the most or front always but on the side we have this which so the results can close even in the but the car so it comes down more subject to ambiguous stuff to identify. And so both of the experiments were conducted on Prolific. It's a crowdsourcing platform. And at each of the experiment, we had close to 120 pairs to compare in a full experiment design. And each pairs were compared by 100 observers, 100 unique observers. We divided also these small chunks for crowdsourcers to be more reliable. The experiment length was a few minutes only, 3-4 minutes per observer. And of course, they were compensated for their effort. And so in the end, we had these are the sample screen from the experiment. On the left, on the right, you make your selection based the left, right. So after introducing these experiments, so we evaluated two inter-observer agreement measurements, let's say, or two. One of them is an inter-observer agreement measure, the Cohen's-Kappa, and the other one is the RT dissimilarity, which is a binary distance metric, basically. Cohen's-Kappa can work with not only binary, but also categorical or other type of data, where Regis-Tanimoto only works with binary data. The values in Cohen's-Kappa can vary between -1 and 1, where 1 indicates a higher agreement among the given observers, a pair of observers, and the values for RT dissimilarity, because it's a dissimilarity, so higher the value, higher the disagreement among the tested observers. And the advantage of RT dissimilarity in this case is it can be accompanied by a weight vector, and this can be used to adjust the impact of each stimuli in the experiment to its impact of each stimuli on the calculation of the unreliability of each observer, which will come in handy, especially for subjectively subjectively more ambiguous tasks. So when we check the two experiments, we also checked how subjective the experiments are from the pairwise comparison results. They're not presented here, but the results indicate that the TMO experiment was more highly subjective compared to view preference experiment, which is also indicated by the mean Cohen-Kappa distribution of the observer population here. And here, each dot represents a single observer, and the mean value of the Cohen's-Kappa of that observer with the rest of the population. So basically, in each experiment, there are 100. So each dot is the mean of 99 Cohen's-Kappa between between an observer I to the rest of the observer in the experiment. And we realized that actually experiment TMO has a lower Cohen's-Kappa, so higher variety in terms of observer opinions. And we saw the same thing on RT dissimilarity, so they have higher RT dissimilarities. and we realized that there are a few observers that that has kind of an outlier behaviors in both measures. Or actually, these are different observers, but I will come to that later. And then we compared actually the measures between the correlation between the two measures for individually for two different experiments. So for a given observers, what is his or her inter-observer agreement with the rest of the population according to RT dissimilarity and according to Cohen's kappa. In the view preference experiment, both measures were highly correlated with each other with a very high Pearson's correlation, and also can be observed from the plot. But for the TMO experiment, there was literally no correlation. This can be explained by the highly subjective, high subjectivity of the task that we have in the TMO comparison. And although this doesn't alone tell which one is a better choice here, but the ability to adjust the importance of each stimuli on the reliability calculations proves RT dissimilarity as a more generally in general, more applicable to this reliability estimation. And to move one step forward, we try to identify, define some spammer behaviors. Also, we refer to the literature to do this. And generally, what is a spammer is can be verbally identified like this. They give consistently unacceptable answers due to lack of attention, or maybe just making money but doesn't caring about the job that they are doing, or simply misunderstanding the task. And the ratio of this type of people in experiment is really high on crowdsourcing platforms because of lack of that control or lack of interaction with the actual observer, and it comes in a cost. It's cheaper, it's more accessible, but it is less reliable compared to a laboratory experiment. And well, some of the tests we have done showed that actually 50% of the data we collected on Amazon Mechanical Turk was rubbish. So you need to be really careful with what you have collected on crowdsourcing platforms. It's not the same for prolific. So based on these observations, what we can define on a binary response nature is 4 types of synthetic spammer profiles. One of them, the first one is random voter. Basically, it doesn't care about which stimuli is or she's seeing, just randomly votes either A or B. And we can easily replicate this behavior with a randomly generating stimuli on any given language that we choose to work with. And we can have a repeater, so can choose always on the left, can be bored, can just want to click on the same place all the time. And it can be inverted, so simply misunderstood the question, which one has the worst quality maybe that they are trying to choose, or simply trying to be annoying, or a mixed combination of all of it. And these also behaviors can be adjusted by an intensity parameter so that we can replicate the kind of behaviors that a spammer shouldn't have to be a spammer all the time. They can go on as a reliable person 80% of the experiment, but get bored at the last few minutes. So then they become reflecting a spammer behavior. So we control the intensity of these behaviors, of these profiles as well. And when we check that influence of the spammer proportions and identifying the spammers based on their mean RT dissimilarity and mean Cohen's kappa coefficients, we realized that the spammer proportions above 30% makes it almost indistinguishable between the spammer and the real observer. And the spammers are for sure spammers because we created them synthetically and added into the real data. And here the dashed lines are the real, solid lines are the real observers, and the dashed line are the synthetic spammers that we added. And on the left side, we have the TMO experiment, and on the right side, we have the view preference experiment. And the top plots are for the RTD similarity, and the plots on the bottom row is the Cohen's-Kappa coefficient values, again, the mean value. And we see that the VP experiment is more forgiving in terms of the percentage of spammers in the population, because it's an easier task. So making an error here is more easily noticeable than a more confusing task, let's say. And similarly, we ran an analysis on the influence of spammer behavior intensity. As I said, we are trying to control this with a parameter for each type of behavior. And we saw that with like 20% of the time having a spammer profile, and for the rest of the experiment acting legally or acceptably, is quite difficult to make it quite difficult to identify. And the higher the proportion of the intensity of the spammer behavior that you are putting, the higher the chance that you get recognized by just the mean value. However, these are really weak tools to conclude that a person is a spammer alone, because we are just checking the mean of each observer's reliability or agreement with another or rest of the population. So from this study, we concluded that the subjectivity of the quality of experience or preference of experience, or whatever you call it, scenario that you have in your hand, is highly important on measuring the observer's agreement. And this also makes it impossible to use a universal threshold with this kind of values to identify spammer profiles. As we said earlier, just a few slides ago, 30% to 40% spammer proportions, which was observable on Amazon Mechanical Turk, makes it impossible to distinguish between spammer and reliable observer profiles. And obviously, simply using the mean agreement is, in most common cases, is not enough to identify spammers. So more sophisticated methodologies are necessary. This was supposed to be a future work at the time of this paper was published, but now it's a recent work, which currently under review. But I have a few plots to kind of show. We ran a large-scale experiment, and on this experiment, we used this tool that we have developed to identify spammers, which was giving a little bit of, I'd say, little bit of hint towards who can be a spammer, and based on your expectations from the reliability of the overall data, we can adjust this spammer threshold and basically select the profiles that we want to reject from the experiment. And unlike other metrics in this scenario, running the metrics several times doesn't give you more and more spammers, because some of the state of the art in this case is like running metrics like 100 times, you can delete all the observers, which is not the case here. It has a fixed number of spammers identified at any given input. So I will hopefully present the recent work in the next week, and then we can move forward from there.
Okay, thank you very much. And it's the time for questions from the online side. Okay, I have a question from the room.
Yeah, actually, I'm curious, is there a more a better way to find the difference between a spammer and an outlier? I mean, an outlier, yeah, also be a good user, but that for some reason perceives something different from the others. So yeah, this is a bit interesting to look at. In this work, kind of the identification between spammer and outlier was, I'd say, there was not a clear distinction, I would say. some outliers were included as a spammer, basically, but some were not because the binary nature of the collected data is also making it difficult to say someone outlier and to say someone a spammer, because most of the time you are either one or not, just like the data itself in this case. So to draw that line, it is really up to your expectations, and you can play with these thresholds and draw the line of outlier or a spammer according to your preferences, basically.
Other questions? You have another question?
As the data collection from subject is always for training deep models are not most of the cases. There is also the case of validation. I would like to know would really those spammers or outlier affect the training strategies, because there are some new area like label noise in machine learning that some outliers in order to make the model much robuster.
Yeah.
So maybe just repeat the question.
Yeah. So I can repeat the question. So is the presence of noise is really important in the large-scale data set cases, because there are some certain models that benefit actually from the label noise when training deep learning models on this collected data. So I understand this concern. Maybe it's not for some certain application. Maybe it's actually beneficial to have label noise. But the ideal scenario would be have a completely clear data and add any label noise if you want on top of it. Because there are certain scenarios that you don't want to have high proportions of noise in the collected data. Always better to have a better data. I don't see a point why you wouldn't want noise in the data. But if you really want to, you can do it by yourself again anyway. So, but there are many applications that we want to clear out the noise from the actual collected data.
No question. No.
Yeah.
Okay. So I just have a small comment, maybe a little bit in the line. Then in psychology, what they do, they always present the results with and without outlier detection.
Mm-hmm.
And I think it's a good, let's say, way that we also should follow.
Yeah.
Sooner or later. Yeah. It actually shows how much the results that we obtain were dependent on the outlier detection. Yeah. Of course, I understand that in the pair comparison case, it's much more challenging because maybe the pairs that you are showing depends on the result that you already obtained, and the result that you already obtained depends on the outliers that you detected previously. So it's nearly impossible to really show the results without the plus. But anyway, at least
in this case, it was not an adaptive pairwise comparison strategy. So the pairs were always the full matrix. So we actually did it in the paper that has been submitted to PMM, but I didn't put it on this slide. But here I put the number of rejected observers basically in each playlist, as we had 50 of them. So you can see there are quite a bit of number of people that has high RT dissimilarity and rejected by the tool that we developed on this paper as well. And of course, this affects the result a bit, but each pair was compared by 70 observers, and we deleted 5 of them. And in the end, the result is not really different. Maybe the significance of the difference between the preferences were not really affected in maybe more than 3 cases. So it might be more important for other cases, but yeah.
Okay. But anyway, I also agree that this is important to clean data. Thank you very much. So next the presentation is from the remote participant from Dietmar. can you hear us? Can you start?
Okay.
Kind of what yeah.
Yeah, I would.
Presentation left we have.
Okay, can I start?
Yeah, we just sorry, we just discussion with Shell about that it's late. I know it's late, but I really wouldn't like to move the sound session just because we have significant number of online participants, I guess, and it's not obvious they can connect or.
Sure. Are you?
Like it's a bit of our fault, like
No.
here. So I would prefer to finish the presentation today. Yeah.
Okay, that's fine.
We're paying for a long lunch. Nice. Yes. So please go ahead.
Okay, so I will share my screen then. Just the application. So I think you should see everything now.
Yes.
Okay, so this is about subjective image quality assessment with boosted triplet comparisons, and joint work by my PhD student Hui Min and my postdocs Hannah Lin and Mohsen Junadeli and myself from last year. And the paper that comes with this presentation was in IEEE Access and from October last year, and it's a long paper, 36 pages, and I can only report a part of it here, of course. So what is it about? The motivation here is that many full reference IQA data sets are published, of course, and they are very important to have when we want to guide some applications like image compression, make it perceptually guided or so. And these IQA data sets are based on original reference images that are usually of high quality, and then they are degraded by some distortion types like blurriness or Gaussian noise or by just compression noise, for example. And the number of distortion levels are typically 3 to 6, as you see here in this table. Okay, and so I think the number 5 here would be representative of the ACR categories from level 1 to level 5, and so this was maybe the motivation to have it at 5. But are 5 to 6 levels really enough? Certainly not. Like content providers, they apply image compression. They want to focus on the high quality range at a level of 1 or 2, maybe 3 JND, but certainly not more. And much of these images and these IQA data sets have very poor quality. So one would like to create better data sets with 12 levels of distortion, maybe even more in the high quality range only. And then we need to sharpen the sensitivity of the subjective assessment. The DCR is the most prominent one there. And our proposal there is to use boosted triplet comparisons. And so I have to explain what this is and show you some examples. So this is a typical DCR experiment setup. You have 2 images, the reference is on the left and the distorted is on the right. I call it the original distorted because we will change it a little bit. Okay, and then the question is, well, on a DCR scale from 1 to 5, is it very annoying or slightly annoying or not annoying, etc.? Most of you are familiar with this. And so our proposal is to boost the differences between the reference and the original distorted one so that they become more visible. So for example, one can do the boosting in the intensity or in the color domain here. So we just amplify the difference between the distorted and the reference by a factor alpha greater than 1. Of course, we clip at 0 and 255 intensities. That's necessary. So that's called amplification. And here's an example. Then we could add zooming, right? Spatial amplification. So when we zoom into the image, we see the artifacts more clearly. And then we can also use the human visual system in the temporal domain. That is, we can add flicker to it. The flicker then would alternate between the one image, the reference, and the distorted one. No, this doesn't work here on my display. Do you see it flickering? I suppose not.
No.
It should flicker, okay. Okay, so this is a problem with the display. So let's just, you have to imagine that it flickers between the reference and the distorted one, which makes it even more obvious. So those are the three mechanisms: amplification of the intensities or color, zooming into the image, the spatial and temporal, having the image flicker between the reference and the distorted, so you don't have to invest the visual short-term memory by moving your eyes from the left to the right and from the reference to the distorted and back and so on. Okay, this is one component. The other component is the triplets. So the boosting was explained, and now the triplet comparison. So we have in a triplet always three images. The one in the middle is the one that the other two images on the side are compared with, and it's called the pivot image in the middle. And the question then that we can ask, which image is more similar to the one in the middle, to the pivot one, the left one or the right one? Or if it's too difficult to decide, then there is also a not sure option here on this slide. Okay, so this is this. And then once we roll this out into the crowdsourcing platform, then the question is, how can we reconstruct the scale values, the ordinal values, or the continuous scale values of the qualities of our sequences of distorted images? And so for this, we use the Thurstonian scale reconstruction approach, but we adapted to the triplet comparison, to triplet comparison. And these are the formulas here, and I will not try to explain them fully, just in a nutshell. So the decision variable would be the Z-ijk. Ijk are the indices of the three images in the triplet, and xk, xj, and xi are Gaussian random variables that have a certain mean. The means are mu. And then we look at these differences, and this is the decision variable. And so this is the random variable. And then the probability that this random variable is positive would then signify a decision that says, okay, the left image is closer to the one in the middle, and one can calculate it using the means of these, or the expectations mu of these Gaussian random variables, and applying the Gaussian cumulative distribution function phi to it in this way, in this formula. This is a formula that was developed by Ennis a couple of decades ago already. So we found this in the literature and apply it here. Then, based on these probabilities, one can write down the negative log likelihood of the responses Rijk for the triplets. So Rijk will be 0 or 1, depending on whether one shows the left or the right answer. If we're not sure, it's 1/2 and 1/2. Okay, so this is a negative log likelihood, and we want to minimize it or maximize it. We want to optimize it. So we have L of mu, and we take the arc min here. The algorithm is here in the pseudocode on the right. So it's more of this is explained in the paper. Okay, so we have now 3 experiments to put this into practice. So the boosting and the triplets and the reconstructions. So first is the basic triplet comparisons, where always the reference image is the pivot. The one that's undistorted is in the pivot in the middle. And the second experiment is where we generalize it, and we have arbitrary triplets. We can put also distorted images into the pivot. And then the boosting can also be applied in the context of a DCR. So we have the reference on the one side and the amplified and zoomed image on the right. We cannot apply the flicker in this sense. And so this was implemented on AMT crowdsourcing platform. And here's the set of 10 images that we used. And for the zooming, of course, we have to define a certain section of the image, half of the size that we pulled out of it to use for this boosting technique. And the green frames here show these parts of these 10 images that we've used here. So these are the 10 source images, and then we have 7 different distortion types. We have color diffusion, high sharpen, jitter, JPEG 2000, lens blur, motion blur, and multiplicative noise. And up here would be the reference image on the upper left. Okay, so then in the first experiment with baseline triplet comparisons, where the reference is always in the middle, we have 8 types of different triplet comparisons, which I'll show you in the next slide. So there's these 10 sources, 7 distortion types, and 13 distortion levels that span a range of 3 J and D. So 2 consecutive images in each sequence have a distance of 1/4 of a J and D. All right, and so this is an example down here. Now, what are these 8 types of baseline TCs? The first one is just plain TC, so we don't do any boosting, right? These are the original distorted images on the left and on the right. So that's only, like Gaussian Gaussian noise was applied, or blurriness was applied. So there's no boosting yet. So then we can apply just the boosting of type A, the amplification, and we use a factor alpha equals 2 here. We also tried others, but 2 was in our choice. So we amplified in color space the distortions. That's type 2. Type 3 is where we just use the zooming, so we zoom and we amplify it again to the full image size, of course. Then we can combine the amplification and the zooming. Okay. Then we have the flicker alone. So the right side here would be flickering, and the left side would also be flickering. So always between the reference and the distorted image, one distorted image, and on the right with the other distorted image. And then the question would be, which image has a stronger flicker effect, right? This is also a triplet comparison. However, the reference is not shown explicitly, but only as a background of these flickering images on the left and on the right. And if the distortion is stronger on one side, then the flicker will be stronger. And this is what the subjects have to decide. 6 would be AF, boosting amplification and flicker. And then ZF would be zooming and flicker. And the last one would be of AZF, amplification and zooming and flickering all together. Okay, so of course we have 3 types of boosting, and so you can apply 0, 1, 2, or 3. That gives you 2 to the 3 cases, 8 cases. So here's the main result of the first experiment. What are we seeing here? We see average results of the 10 over the 10 sequences and all of the distortions. And we have 12 distortion levels. So here at 0, we have the original, and at 12, we have the heavy, medium distorted image at 3 J and Ds. And when we use just the plain TC, the lower dashed curve here, the black dashed curve at the bottom, it starts at 0 impairment and goes up to 3. That's 3 J and Ds, and it's a straight line. So we, in the pilot test, we chose those distorted images to come up with this result. This was by design and not just by coincidence. And then the other curves here show the measured or the reconstructed impairment based on the Thurstonian reconstruction when we apply those other 7 types of triplets or boosting for the triplets. And you see that the curves generally have a larger slope here initially, and then they ease off. And then the strongest improvement then is given by the combination of all 3 methods, A, Z, and F. So for a distortion of half a J and D, which is at distortion level 2, the AZF boosting will give us 4.3 J and Ds already, a much stronger and more often observed distortion than without any distortion. So we have a higher sensitivity here. Okay, talking about sensitivity, we should like to quantify it. So we introduce the sensitivity gain. This is the factor by which an increase of the perceived distortion, let's say here, the blue curve here is the perceived distortion as we increase the distortion level using plain triplets, so without any boosting. So it's a nice linear curve by design. And so when we go from one distortion level to the next, we get a little bit of increased impairment, perceptual impairment. And then if we use a boosting technique like the AZ boosting here, that's this curve here on the top, we get a larger increase. So the factor by which this increase is multiplied is our sensitivity gain. So a sensitivity gain of 2 means that locally, when the distortion gets heavier in the originals, then we have amplified this distortion, or this distortion gets amplified by a factor of 2. All right, and then the fat red line here gives us the distortion, gives us the sensitivity gain of as a function of the distortion level. So we see that there is a sort of a cutoff here at between 5 and 6 distortion level, where before that, for the very small distortions, we have a high gain in sensitivity, and later on the sensitivity gain is less than 1, indicating that the boosting technique does not work so well for these highly distorted images here. This is for the AZ boosting, and if you look at all the other types of boosting, we get the sensitivity gain curves here on the right, and so we see that most of the methods will give us a gain of like 2, 3, even 4 or more for low distortion values up to maybe 1 JND, and then it eases off. Okay, so we have the saturation effect here, and we would like to eliminate it, and our proposal then would be to use the general triplet comparison, where we don't have the reference image in the middle, but others that are closer to the distorted ones. So for this experiment, we narrowed it down just to 2 types of triplet comparisons, so just a plain without any boosting, and then the strongest one, AZF boosting. And we again use the same 10 sources, but only 1 distortion type, motion blur. And to make it harder, we use 30 distortion levels instead of 12. So spread over a range of 3 JNDs, the spacing between 2 consecutive test images is only 1/10 of a JND, a very, very small increase of distortion. Okay, so this is for the plane, and then this is for the AZF boosting. So here we have 2 images, and they should be both flickering, which you don't see, unfortunately, and the stronger flicker effect should be identified by the subject. Now, here's the main result of this experiment. In blue is shown the experiment result for the plain triplet comparison, so without any boosting. And so for the very small distortions, distortion levels 1 to 3, so where we have only a few tenths of JND, it is very hard to identify any distortion, and then it eventually climbs up to 3 to 4 here. But when we do the boosting, the red circles here show the boosted curve. We see a very nice clear curve that moves up, and then the sensitivity gain, which is the solid red curve here, starts above 35 and is always well above 1, even above 5. So over the whole range of distortion levels, we have an amplification factor of 5 in the sensitivity gain here. So that is very promising. But we can also look at other aspects. So we can look at the true positive rate. How likely is it that a subject would identify the correct site in this triplet comparison? And it's much better with, the likelihood is much higher for the boosted triplets than for the plain triplets. This is what's shown here. We have convergence in precision. So the precision of the reconstruction for a given budget of triplet comparisons can be measured by the 95% confidence interval. So here we see how the confidence interval, the average confidence interval at distortion level 5 here goes down as we increase the number of triplet responses per sequence. So we randomly sample 2,000 or 4,000 of these responses, calculated the confidence interval of the reconstruction at level 5, and both for plain and for boosting cases, and we see here orders of magnitude difference. And so the take-home message here then would be that 10,000 triplet responses for the plain triplets give us a precision which equals the precision we would have gotten only with 400 boosted triplet comparisons. Okay. Also, we can consider convergence in ordering. So here we look at the SROCC of the sequence of 30 items, And we see that the blue curve is the convergence of the SROCC as we increase the number of triplet responses, random triplet responses per sequence. And the red curve is for the the boosted case. And so to get the performance of plain triplets obtained with 10,000 samples, we only have to use 50 samples with boosting to get the same SROCC. So this also is a nice result. Now the last experiment, just quickly, this can also be applied just to the plain old DCR technique. So we used 4 types of DCRs: the plain, amplified, zoomed, and amplified and zoomed with the 10 sources, all distortion types, 13 distortion levels again. And so just like experiment 1. And then the main result is this. The blue curve here is well, not the reconstruction, but the DMOS then, of course, for the different distortion levels. And so this climbs up here to 4 or 5. And then the red curve here gives us the DMOS for the DMOS for the boosted case. And then here's the sensitivity gain. And we also have a sensitivity gain, which is larger than 1. But only for small distortions up to 0.75 JNDs. Okay, so finally, I'm almost done. So finally, we have put this together into our data set, and now we have the data set config IQA part A and part B with from experiment 1 and experiment 2. And we have this now with 12 or 30, even 30 levels of distortion. And you can compare the different data sets by looking at the resolution of them in terms of distortion levels per decibel and PSNR. And then we see that most data sets down here have PSNR values that are way below of what's interesting for any practical applications, like below 25 is a very poor quality. And our 2 data sets here have a much higher resolution in terms of levels per decibel in PSNR. Okay, the conclusion now, last slide. So we introduced 3 boosting techniques, anti-artifact amplification, the zooming, and the flicker. We didn't invent any of these, I think, because there's some people have used these. Zooming is a natural thing. Flicker is also already contained in a standard for JPEG XS. And then we enlarge the sensitivity of pair and triplet comparisons and increase the accuracy of subjective full reference IQA. So the reconstruction works with Swathonian probabilistic models and maximum likelihood estimation. We generated 2 IQA data sets of over 1,000 images, and provided this extensive performance analysis. We have the ratio of true positive responses, detection rates, sensitivity gains, effect sizes, convergence and accuracy and correlation, and also time complexity, and I didn't show all of it. So that concludes the talk. Thank you very much for your attention.
Thank you very much. Thank you for speeding up at the end. Yeah, very interesting talk. I see, are there any questions from the room? I think there is an online question, if I understood correctly. Let's check that.
I don't see a question in the chat.
Anna Flores raising her hand.
Yeah, Anna Flores raising hand.
Hi, thank you for the interesting talk. I actually have a question because I actually don't know how you go from your rating scale to the GND paradigm. Could you tell us a bit more?
So would you like to know how to calculate the JND scale from ratings?
Yes, please.
Okay, so well, the JND scale is defined from the Swathonian probabilistic model. So the model says that we have Gaussian distributions, and then when we compare 2 stimuli and try to detect a difference, then you present them side by side, and then the user has to say which one has the better quality, essentially. So, and if the qualities are indistinguishable, they will have to guess, and they will say left or right arbitrarily. Let's forget about the not sure option here for this explanation. So 50% is always something that you can get right just by guessing. And then the J&D happens when the two distributions are so far apart, so the difference of the means are so far apart that 75% of the people will click on the correct decision. They will identify which of the two stimuli has a stronger distortion. So this is how you can set the scale to the J&D, right? Now, when you apply the usual Thurstonian reconstruction, you have to be a little bit careful, because normally what people do is they just say that the variance of the distributions that they use for this model is 1/2, and so the variance of the difference of two Gaussians is 1, then that does not, when you just reconstruct from this, you have to divide by 0.6475, I think, to get to the J&D scale, as I explained it. But this is all very straightforward if you just go by the principle that a 75% correct decision rate for a pair comparison will define the level of one J&D. Did this answer your question?
Yeah, really clear. Thank you very much. Actually, if I can ask another question, how do you deal with the tides with your unsure answer?
Oh, I didn't get the question. How do I deal with the types of what?
With the tides when someone answers, I am not sure.
Oh, the ties. Okay, sorry. Okay, the ties for the reconstruction. The reconstruction first works without the ties. So I explained that in the probabilistic model, for the reconstruction, we use the maximum likelihood estimation. And so we have a probability for a left answer and a probability for the right answer, but not for the not sure option. So what we do is the following, a very simple hack, if you like, but it works very well. Although there are some people that debate about this. The hack is that every answer is duplicated. So every right answer comes up twice. So each triplet would be counted twice for the right answer and for the left answer. And for the not sure answer, we also generate two triplets, and one would answer left and one would answer right. And that sort of evens it out. So that's a recipe of how to do the reconstruction with the not sures.
Okay, thank you very much.
Sorry, Adeyemi, but we cannot hear you.
Yeah, I didn't say anything. But I'm reading the question. There's a question in the chat. What would you recommend when the impairments are all coming from cameras? It is more difficult or impossible to align the images. Okay, so I think this is something that is not covered yet by this paper, but it is addressing something that we are interested in and pursuing right now. This is similar to what if you have mixed distortions, like all kinds of combinations, and also distortions by different cameras. So there is not a one-dimensional continuum like increasing Gaussian noise, with one parameter. But if we may have many parameters, and we all have these images all in one bucket and need to order them at this simultaneously. And for this purpose, I think one can still do the triplet reconstruction and also use any of these boosting methods. However, for the reconstruction, one has to have a better method. And what we believe in is that we have to go into a multidimensional setting where we allow several dimensions for the reconstruction and then map that back to a one-dimensional scalar quality. So this is work for the future that we're currently doing. someone is saying something, but it's too choppy. It's not arriving at my end.
We have one last station. I don't know if we can actually say that that we switch to another presentation, because I'm not sure if we are ahead.
Yeah.
Sorry?
The comment. You cannot hear.
Ah, yes. We hope that at least people online could hear it. And we have to move to the last presentation. Do we have the presenter here?
Yes.
No. Yes. So,
Hello.
please. Hello.
Hello.
Maybe what we could try to do is to use less network in the room. Like we can disconnect our Zooms. Yeah, disconnect our Zooms, for example, as well. Yeah. Because I think this is the main source of the problem. Well, so let's say that at the end, someone has a question, and just please, from the online group, just please ask this question. All right.
So can we start?
Yes, please go ahead.
All right, thanks.
Okay, hello everyone. Nice to meet you here. It's my pleasure to hear so much excellent research, and I'm glad to introduce the subjective test analysis tool that we implement. And please change the.
No, I'm changing the slide, but
Okay,
changing the
sorry.
slide, but it's not appear.
Here. So firstly, please let us to introduce ourselves. We are 3 students from Polytech Nantes, major in computer science. My 2 teammates are Sharma and Ivan, and my name is Jiawan. 8 months ago, we followed our school's guideline to attend this transversal project. We chose the title Subjective Tests and Metrics in Video Quality and Evaluation, Repeatability and Precision. And we are guided by our client, Ms. Penson from the Institute for Telecommunication Science in America, and our tutor, Mr. Gale from LS2N laboratory. Our goal is to create a centralized tool that allows users to use several statistical tools on subjective test data set and analyze them. So to be more specific, this UML shows globally the usage of our analysis tool. A user should first input his dataset with some simple description. That will help our system to formalize users' dataset structure. They can also choose one from the dataset provided by our system. Then the users can choose different statistical tools like mean opening score, confidence interval, and so on to apply on the dataset and see the analysis result.
So this is the homepage for our tool. It was coded in Python using for the user interface the TechInter library. So as you can see on the homepage, there is a navigation bar that allows the user to change between the different parts of the tool. The homepage presents the user with two options, which is either to use their own data sets or use a data set that we have. The data sets that are present in the tool are University of Nantes data sets that date from 2015. And since the goal afterwards is to run different statistical analysis on the data sets, we decided to formalize all the data set in the same format, which is a format that we found several times within our University of Nantes datasets, and we call it the standard format. It's as shown on the picture. All the stimuli are lines, and the observers are in the columns. And at the intersection between the line and the column, we get the individual scores for given by an observer. We also have the ability to select a subsection of the data sets. For example, if you only want to run an analysis on a couple stimuli or a couple of the observers, this option is possible. And also, obviously, the user can add their own data sets that they gathered themselves. And for this, since all the data sets can come in all different formats, we've decided to give the user a way to use different structure of data sets in the tool.
So indeed, this is an important part of our tool to be able to ingest different data sets that the user can add. And so for that, you select a file, and then it tells you the name of the file you've chosen. And if it's an Excel file, you can even choose which sheet you want to use. And so to be able to ingest this data and to put it in a format that all the statistical tools that we implemented can be used, we need three mandatory attributes. The first one is the name, the stimuli. The second is the observers, and the third are the ratings of the stimulus by an observer. So it can be column or it can be rows. We will see that here. So when you select your data set, you're then presented with this. And within this example, we can see that we indeed have the three mandatory attributes. Here with test subject, we have what corresponds to observers. With file, we have what corresponds to stimuli, and with scores, we have what corresponds to ratings. So here, with the buttons on the right, you can select which column or rows corresponds to what attributes. And when you've selected that, our program will then process this information and transform the dataset in a way that can be used by our statistical tools. So now going to the statistical tools. So for now, we have a selection of statistical tools that are shown on the right. And when you select an option, you are then given a little description of what the point of the tool is, and also what's kind of happening inside the tool. Currently, we have a simple
MOS or for the stimuli. We also have precision of subjective tests for ACR5 and ACR 100. Those two were provided to us by Margaret Pinson, who gave us the MATLAB code, and then we put it into Python. And confidence interval and accuracy were provided to us by Yana Neme, and those two were in R code, so we put it then into Python. And so when you've selected which statistical tool you want to use, you can then get the results. So here are some example of results. So the result can be either directly in a file, like in an Excel file. Here we can see the MOS for a file with a lot of stimuli, or it can be a graphical result with graphics. And for the both of them, you have the choice to save the results either as a Excel file or as a PNG or JPEG to keep trace of the result. And also one important thing is that what we've been working on, the code of what we've been working on will be available on GitHub. So then people will be able to add their own statistical tool and add directly more that available data set directly to the tool if they want to. So this concludes our little presentation to end the day. So thank you all for listening to us.
Thank you very much. Any questions? You said it will be available. Do you have any date, right?
So this, so like we said at the beginning, this is a project that we are doing for our university. So normally we should have finished it completely, I think, in 2 weeks. In 2 weeks, we should be able to share the GitHub.
I would really appreciate if you send it to the thumb reflector, the information, because this could be interesting for more people.
Okay.
Now, and especially more people could be willing to participate and add something. And thank you very much for your effort and for making it.
Thank you.
Right. Are there any questions from the online audience? I cannot see it here, so if you have any questions or comments, just go ahead. Assuming that you can hear us. Okay, thank you very much. Yeah, and this is the end of the SAM session. Sorry that it was so long, but I keep it in one piece. And
so we have one thing more before we end for today. Is the minute. And stop the recording.
The recording was stopped.
It's on the top
Maybe
corner.
Press plus. Oh,